Okay, now that we've learned about the rules for quantum numbers, I want to take you through the quantum numbers for the shells 1 through 3. Now, remember that n can have values of 1, 2, 3, and so on. And to figure out how many orbitals we have, we can square the quantum number n, or we can just figure it out intuitively from L. L can be 0, 1, all the way up to n minus 1, and that's how we'll mostly use it. Now, how many electrons can fit in each orbital? The answer is 2. It turns out that the spin can be plus a half or minus a half, and so each of these two electrons, if they have opposite spins, can reside in the same orbital. We won't specifically memorize this formula, but we'll see how the number of electrons in the shell can be equal to 2n squared. All right, so let's look at the first shell here. When n is equal to 1, we know that L can be 0, and that's it. It can vary from 0 up to n minus 1, so L is equal to 0 only. We describe this electron cloud as an s orbital, and we could compute the number of orbitals here by taking 1 and squaring it, and we get 1. So we know there's only one orbital in the n equals 1 shell. Now, there are two electrons that can reside within this electron cloud if they have opposite spins, and so there's just going to be 2 electrons here. You could compute this. We have 1 orbital multiplied by 2 is 2. All right, and there's a total of 2 electrons in this shell, therefore, we don't really need to go through this 2n squared, but 2 times 1 to the second power is just going to be equal to 2. Now, how about the n equals 2 shell? Now here, remember, L can vary from 0 all the way up to n minus 1. So it's possible for L to be equal to 0, and it's possible for L to be equal to 1. Now, if L is equal to 0, we call this an s orbital, okay? Once again, the s orbital has just this single shape, and there's 2 electrons that can fit into it with opposite spin, and there's a total of 2 electrons in that subshell, all right? Now, when we're talking about the L equals 1, we have the p orbitals. And you might be wondering, well, wait a minute, why are there 3 p orbitals here? Let me refresh your memory about the quantum number m sub L. M sub L varies from negative L to positive L. In the case of the s orbital, you just have one possible orientation. ml is equal to 0. There's only one orientation, and that's it, that blue sphere. Now, when L is equal to 1, ml can be negative 1, 0, or ml could be positive 1, okay? And these are 3 different orientations, 3 separate orbitals, okay? So when you look at these, there's going to be 4 total orbitals here, okay? There is 1 s orbital and 3 p orbitals for a total of 4, and we could also calculate it. 2 squared is equal to 4, okay? 2 times the quantum number n squared, n quantum number squared is going to be equal to 4 when n is equal to 2, all right? So, but I think it's easier just thinking about it. When you have L equals 1, you always know you're going to have 3 p orbitals. Now, for the first px, you can have 2 electrons in that. The middle one here, py, you could have 2 electrons in it. And the pz, you could also have 2 electrons in that. So there's a total of 6 electrons that can reside in the L equals 1 subshell, all right? Overall, there's a total of 8 electrons, 2 from the s, 6 from the p, so a total of 8 electrons fit or fill the n equals 2 energy level. We could also calculate this using the 2n squared formula, and we get the same number, 8, all right? So far, this is our summary table. For the n equals 1 shell, we have s orbitals only, and there's 2 electrons in that s orbital. For the n equals 2, you have s and p orbitals. So there's 2 electrons in the s orbital and a total of 6 electrons in the 3 p orbitals, giving you a total of 8 electrons in that shell. Now let's go on and work with the n equals 3 shell, okay? Now for this principal quantum number, L can vary from 0 all the way up to n minus 1. So when L is equal to 0, we call this the s orbital, and we've seen before there's 2 electrons in there, and that's it. L can be equal to 1, and we've seen this before. There's 3 different p orbitals for a total of 6 electrons, 2 in each of the orbitals, okay? And we've seen that before. Now, what do we do when L is equal to 2? This is something we haven't seen yet in this video. We have what are called d orbitals, okay? D orbitals have these kind of like cloverleaf shapes, except the one in the middle, which kind of looks like a dumbbell stuck inside of a donut somehow. Now, remember that ml can vary from negative L all the way to positive L. So let's take a look. M sub L is minus 2, and you have 2 electrons in that orbital. M sub L is equal to minus 1. We have 2 electrons there. ML is equal to 0. We have 2 electrons there. ML is equal to plus 1. We have 2 electrons there. And ML is equal to plus 2. There's 2 electrons there. Okay, so ML can vary from minus 2 all the way to positive 2. And, whole numbers in betweens. That's a total of 5 d orbitals. 2 electrons in each of those 5 gives you a total of 10 electrons in the d orbital, or the L equals 2 subshell. That gives you a grand total of 18 electrons in the n equals 3 shell. You could also calculate it using that 2n squared formula. 2 times the principal number, n, is 3 here. So 2 times 3 squared is 2 times 9, or 18. So that's how you could easily calculate it without, going through and understanding much about the orbitals there, okay? Now, how do you count the orbital types? Again, we saw that there was one s orbital, there were 3 p orbitals, and there were 5 d orbitals. So 1 plus 3 plus 5 is 9, and we could also calculate it using n squared. So 3 squared is 9. So that's a neat little trick to just quickly figure out, well, how many orbitals do you have, all right? So here's our grand summary chart showing the shells for n equals 1, 2, and 3. You can see how as you go to higher energy levels, you begin to occupy P and then D and then eventually F orbitals, okay? And I've tallied up the number of electrons in each of these subshells, okay? So, and then the total electrons in each shell. Now, before I leave, I just want to take a peek at the periodic table here and look at element 118, oganesson, okay? This scientist is still living, and he is honored by having his name on the periodic table. Now, if we look at these numbers on the right-hand column of this element symbol from ptable.com, we can see 2, 8, and 18. And look, n equals 1, there's 2 electrons that can fit in that energy shell. When n is equal to 2, there are 8 total electrons that can reside in that energy shell. And when n is equal to 3, there are 18 electrons that can reside in that energy shell. So we'll begin looking at the periodic table next and figuring out where these sublevels and levels and shells and subshells are located and talk about the octet rule. So for now, I hope you have a greater understanding of quantum numbers and how the shells are filled up. Thanks for watching, and please subscribe.